In this video, we are going to do a graphical example involving derivatives. So we have this graph here, and it goes through a couple of points, 2, negative 3. It goes through this point 0, negative 2. That's the y-intercept. It goes through 1, 0, 1, 0, and then it goes through the point 2, 2, and then it has this horizontal asymptote. Part A asks us to find all the x values where f prime of x equals 0. So remember, f prime of x represents the slope of the tangent line. So this is saying we want the slope of that tangent line at x, whatever the x value is. We need that slope of that tangent line to be 0. So let's put a little circle around this. If the slope of a line is 0, that means that line is horizontal. So I got to identify what points on the graph will I have a horizontal tangent line. That's a point on the graph that seems to get sort of perfectly flat. So I want you to pause the video for 30 seconds and see if you can identify where those are and draw in those tangent lines. 4, 3, 2, 1, pause it and see if you can identify where that happens on the graph. All right, let's talk about it together. So one such point is at 2, 2, this high point. The graph gets perfectly flat there. So my tangent line will look something like this. Perfectly horizontal. The other point is at negative 2, negative 3. The graph gets horizontal momentarily there. Perfectly flat momentarily. So I have a horizontal tangent line. Okay, so the answer to part A is it happens when x equals negative 2 and when x equals positive 2. All right, we're on to part B, which says let's find the average rate of change on the interval from negative 2 to 2. So recall our formula for average rate of change. So I will abbreviate and write AROC for average rate of change. So this is just the change in y over the change in x. So the y values at these 2 points are going to be f of 2 and f of negative 2. So I got to subtract those y values, and on the bottom I subtract x values. 2 minus negative 2. So I see that the y value at 2 is 2, and then minus the y value when x is negative 2 is negative 3. And on the bottom I get 2 plus 2, which is 4. I got double negative becomes a positive, so I get 5 over 4, and that's my average rate of change. Okay, so we're on to part C, which says, well, which is larger now? F prime of 1, or f of 2 minus f of 1 over 2 minus 1. So I want you to pause the video one more time to try this. Pause it for 2 minutes to try this question. 4, 3, 2, 1, pause it and try this one for 2 minutes. Alrighty, so hopefully you've done that. Hopefully you've paused it and tried it for about 2 minutes. Let's talk about it together. So remember that the derivative, in this case it's the derivative at 1, represents the slope of a tangent line. So this is the slope of the tangent line at x equals 1. So if we draw that in, actually, you know what, let's state what the other side represents and then I'll draw both of them in. So the other side looks like my average rate of change in part B a little bit. It's a change in y values on top over a change in x values. That is a slope of a secant line. This is a slope of a secant line between, I'll try B, T, W, N to abbreviate between the point 1, f of 1 and 2, f of 2. So let's just draw on those lines and see which one has the bigger slope. So let's start with the secant line. Okay, so here is the point where x is 1. Here is the point where x is 2. If I connect them with the secant line, it's a straight line connecting them, I get something like this. So that is a secant line. So now if I think about, well, what would the tangent line at that point look like? There are a few ways I can think about this. One is if I were to take the point that's at 2, 2 and start to move it closer to the point where x is 1, would it make my secant line steeper? Or would it make it flatter? So if I just visualize that a little bit, if I move this point closer and closer and closer to 1, 0, it will make it steeper. So my tangent line will look something like this. I might also just try to draw it and try to find a draw it in such a way that my tangent line kind of matches how steep the graph is right at that point. But this pink line, this is my tangent line. And that slope is bigger. The other way that I could tell from this picture that the tangent line is going to have a bigger slope is if I think about the slope at the point 1, 0, and then if I were to think about what happens as I move right closer to 2, 2. Well, the graph gets flatter. It gets flatter and flatter and flatter until it gets perfectly flat and horizontal at the point 2, 2. So over time, the slope is getting smaller. And that's another way I can see that the tangent line is going to have a bigger slope than the secant line. All right, so let's state the answer now. So f prime of 1, the slope of our tangent line, is larger. All right, and part D is a more graphical question. It wants me to draw a rough sketch of the derivative graph. So I've recopied the original functions graph, and I'm trying to draw a sketch of the derivative graph now. So the idea I'm going to use is I'm going to make a sign chart of the derivative. So I'm going to make a number line. And I know from part A, the places where my derivative equals 0. Remember, there was a horizontal tangent line at when x is -2, and there was another horizontal tangent line when x was +2. So I'm going to put a tick mark where x is -2, and I'll put a tick mark where x is +2. And at those 2 points, my derivative, its value is 0. It's 0 at both of those points. Okay, in between -2 and +2, if I were to take a point, say on the graph, in between those two, notice that if I were to draw a tangent line, it would have a positive slope because my function is sort of going up. It has this positive slope. So I'm going to put a positive sign because remember, my derivative represents the slope of the tangent line. So in between -2 and +2, the slope of any tangent line that I draw is going to be positive. Okay. And on the flip side, if I were to pick a point, let's say to the right of x equals 2 over here and draw the tangent line, that tangent line would have a negative slope. So I'm going to put a negative sign here to indicate my derivative, my slope of my tangent line, is negative. Similarly, if I were to pick a point that's to the left of where x is -2 in the original function graph, like over here, that point is having a negative slope if I draw the tangent line. So my derivative is going to be negative over there. Okay, so let's use the fact that I know these signs to now draw a rough sketch of my derivative. Okay, so y equals f prime of x. Let's zoom it out a little bit more. All right, so I'm going to draw some axes, draw a y-axis, draw an x-axis, and let's put some tick marks. So I'll go 1, 2, 3, 4, 5. Then I'll go -1, 2, 3, 4, 5, -5. Okay, so I know that my derivative needs to be 0 when x is -2 and when x is +2. So when x is +2, the output needs to be 0, and when x is -2, the output needs to be 0. In between those numbers, my function is going to be positive, my derivative is going to be positive. So I'm going to start to draw it kind of being positive here and being positive here. These outputs, these y values of my derivative graph are positive. It'll be a little bit helpful if I can figure out on the original function graph, where does it seem like the slope is biggest? And I would say that seems to happen maybe here-ish. This seems to be the point with the largest slope tangent line. So that x-coordinate seems to be around 1. So on my derivative graph, it should be kind of highest at 1. So maybe let me make a more accurate picture. So that portion of the graph might go something like, and has its highest point at 1, and then it dips down. Something like that, maybe. Something like that. All right. And then if I look at the original graph, from where x is 2 going to the right, the slope is negative, but it's not that negative because it's still pretty flat. So on my derivative graph, I'm going to draw values that are negative, so negative y values, but I don't want them to get too small because in my original function, the slopes of those tangent lines didn't get too steep. Shows to stay not too low. So maybe something like this. Okay, on the flip side, when I look at x equals negative 2, and I go to the left of that, when I go this way, the slopes of those tangent lines get more and more and more negative. So on my derivative graph, over here to the left of negative 2, these outputs need to get smaller and smaller and smaller. So it's going to be something like this. All right, and that is the graph of my derivative. Eventually, when we learn about something called a concavity, we'll be able to use that to draw a more accurate picture. That'll give me more information about, well, when is my function going up and when is it going down and how is it curving? But for right now, the key idea was that when the slope of my tangent line is positive, my derivative graph should be above the x-axis. When the slope of the tangent line is negative, like it was at these ends, my derivative graph should be below the x-axis. It should have negative y values. All right, so returning to our goals, we finished the last 2 goals in tandem in this last video. Learning how to draw a derivative graph when given the graph of the original function, and being able to compare average velocities, which are slopes of secant lines, to instantaneous rates of change, which are the slopes of the tangent line.